Okay, so probably a little bit early, 5 minutes later, so I gradually start my talk. And well, first I have to say that yesterday there was, after my talk, many people came to me to ask some questions, but there was not enough time for discussion. So today I want to leave some time for this question and answer after my talk. And also, it is time is limited for individual questions, so it may be better to ask questions after my talk. Just raise your hand. And also another announcement is today there is two parts, and originally the first part is for the data-driven method in material science, as I have shown here, and the second part is systematic parallelized experiment. But probably it's better to shorten somehow, so I have rearranged my content, and I will include this systematic parallelized experiment in the first part. And in the second part, I will talk about something called machine learning potential, which is based on first principles of calculation, but it's quite useful for large-scale simulation. So that is something, kind of announcement. So let me start. The first part of my talk is related to the recommender system, which I have somehow talked yesterday. That is quite often used in e-commerce. And this was already I talked about the traditional way to discover new compound based on similarities. And we expanded this method in some way to be able to include many features. So this is 500-dimensional space, and we put all these data registered in ICSD. And again, we made a grid in this 500-dimensional space to have this initial data. Then after classification, binary classification technique, there are many different kinds of binary classification technique, and there is no clear logics. But if the prediction works nicely, it means the validation is successful, then it is a classifier. So we found that these three classifiers are quite useful, and we did that this random classification works the best. This was what we obtained and get to the experimenters. So those are summaries of what I have talked yesterday. And I will talk a little bit more about this recommender system, and that is an improvement of the recommender system using the modern data science technique. And the method is called tensor decomposition. Other than the method, the purpose and also the database are the same. Okay, so in the recommender system, like in Amazon.com, they have a huge list of customers. This is the user's item purchase record. And in case of Amazon, the number of users or customers is sometimes billions over the world, probably more than 1 billion, because Amazon is doing very good business. And there's a huge user list, and they know who bought which item. It's a huge, this is matrix, and based on that data, when some new customer comes, they recommend something and for the target user, estimation of recommendation scores for that target user, so they perform pinpoint advertisement. That is the system algorithm behind it. So we use this technique for the search of CRC, chemically relevant composition. The technique is very simple. This is the rating matrix or customer's purchase record. And what they do is based on the assumption that people with similar taste tend to buy similar items. This is unsupported assumption from the mathematics or from the physics viewpoint, but in the social science, well, it's quite acceptable. All people have a similar taste. If your friend has a similar taste, well, she or he may be interested in the similar product. So that is unsupported but quite reasonable assumption. And based on that assumption, this is in the mathematics language, it is called a low-rank structure of this type of matrix, rating matrix. If this works, then we can decompose into this matrix into a few smaller matrices. And then after this was made by just rearrangement of these matrix elements. So the customer list here is A, B, C, D, E, but here is changed A, C, H, B, something, and also items are different. So the orders of each element are different. But in that way, and we can understand that A, C, H, those customers have similar taste. So probably this customer A and C is interested in buying this product number 3. The similar thing is for the customer H for item 2. This is a matrix decomposition. So we try to apply this to the search of chemically relevant system composition. The candidate of chemical space yesterday was something like 1.8 million. We try to extend that to larger chemical space. So we have chosen the ternary system with A, B, small character A, B, C with this ratio up to 8, then it becomes 7.4 million. In the case of binary with 5 elements, and this small number is less than 20, then it becomes 23 billion. It is a lot of combinations and a huge chemistry space. They are composed of 66 cations shown here and 10 anions shown here. So we restrict for the ionic systems there. So this is our search space, which is larger than the one I had shown yesterday. Compare with those candidates. Candidate is something for 7.4 million or 23 billion. Compare with that. Our database is very limited, but this is the only database available and we can use, so there are no other ways. We need to use them. So there are, you can see that there are many orders of difference, but to search this space, we use this data. And also, there is a huge overlapping between different databases. The similar to the talk yesterday, we use only ICSD data for training, and for the validation, we use this pink area, ICDD or shipping material, which is not included in ICSD as a test set. So these are number of data in a test set. So let's see what happens. So instead of using the rating matrix, we will use tensor. And the tensor is composed of like that, cation type, anion type, integer set in this case. This is for the binary case. And so binary material contains less than 1 million, just 110,000. But this is third order tensor. If you increase the number of elements, then it becomes fourth order, fifth order tensor, which is not easy to graphically shown. So allow me to explain with a binary system. And they are all in a categorical data, so it's not a value, but just is a number, not a number, is a character or category. Also the integer set. This is not used as a percentage or something, but just a category. So for example, TS304 is a material located here, which is composed of Ti as a cation, oxygen as an anion, and the 3 to 4 as an integer set. For the tensor factorization or tensor decomposition, there are many, many different techniques. And especially these days, it's become quite popular because of the emergence of big data analysis. And there are many methods available, but among them, this two methods, canonical, polyadic, and higher order singular value Tucker decomposition techniques are thought to be quite useful. And we tested both. By the way, they are available in software, open software called Psychic Tensor. So we can just download and use them. We found that Tucker decomposition works much better. The Tucker decomposition performed that this is a huge tensor, and it decomposes to this small tensor. This is called core tensor with 3 matrices. So in that way, tensors are decomposed to small tensor. So let me show the result or performance of Tucker decomposition. So this figure shows the horizontal axis corresponds to the length of this core tensor. So there are 4 numbers here because this is fourth order tensor for the ternary system. And the vertical axis corresponds to the number of correctors. I forgot to switch on the stopwatch. So vertical axis corresponds to the number of correct answers included in ICDD and Springer material. So it means number of correct answers or success rate. The yellow or orange one corresponds to the top 100 composition with high predicted rating from rank number 1 to number 100. So firstly, I found that this is almost independent of the choice of land. So the result is more or less similar. And also the number of correct answers were something like 50 to 60. So this is only within top 100 candidates. So it means discovery rate for this case is something like 59%. This is really surprising to us when we did this analysis, because remember that what we did is just exchange elements. No elemental features, no prior knowledge, no solid state chemistry knowledge, nothing used, no first principles result used, just by exchanging the elements. then we were able to find such a high discovery rate. It is the same for this blue one. Blue one is for top 3,000 compositions with high predictive rating. Still, the discovery rate was more than 25%. Yesterday, I talked about the recommender system with elemental features, 500-dimensional space using electronic activity or atomic number or so on. And at that time, discovery rate was something like 15%. Even 50%, we were so happy and gave the data to the experimenters. But this tensor decompression performed much better than the previous method. So this works quite nicely with it is not only for the ternary system. This is, again, the vertical axis corresponds to the number of correct answers. This is the number of samples from top 1 to top 100. The success rate, top 100 was 59% for ternary. For quaternary, it was also 52%, not so different. But for quinary system, it was lower, 15%. We know the reason for that. It is because the number of input data is much smaller in quinary system. Because quinary system, people do not want to do such a complicated compression to do experiment or just mix up many elements to find out some new material is very time consuming, so people do not do much experiment for the quinary system. So they did more experiment for ternary system. That's the reason why the quinary system data is limited. This is just up to top 100, but so it corresponds to here. The tendency is more or less similar up to top 3,000 ranking. But the 15% of success rate for quinary system is still quite satisfactory because we have to handle for the quinary system 23 billions of combinations. And to search something in the 23 billions of the world without any prior knowledge or without any indication or without map is very, very difficult. Even 15% of knowledge should be very useful for quinary system review. So for us, when we obtain this result, of course we want to confirm that these results are good enough or not. Of course, one way was to examine them in the test set. If the test data is available in the test set, of course we judge that as a clinically relevant compression. But the other way is, of course, one way is to do a systematic experiment, but to perform millions or billions of experiments is not practical. So instead, we use first principles calculation to examine whether they are dynamically or thermodynamically stable or not. Because for us, the first principles calculation is a kind of routine. This is a further investigation by first principles calculation for pseudo-binary compound with high predicted rating. In rubidium oxide, indium oxide, we found two pseudo-binary compound which shows quite high predicted rate, but they were not yet reported by experiment. So we did systematic first principles calculation for this system. This is rather busy picture, but the conclusion is that both of these two materials were found to be located on the convex arm, something like this. So they are confirmed to be thermodynamically stable. let me explain a little bit more about this picture. There are many, many dots here. All of them correspond to the one first principles calculation structure optimized first principles calculation to get this formation energy. But the difference is the different structures. And we took many different structures from the ICSD database. ICSD has many different, they registered many different structures for example, in this case, 112 type of chemical compression. Then we took all of those structures and optimized the structure to have energy. The one of the lowest energy one was located here. We had to do that because we did not know the chemical structure of this material because this was not yet reported. Excuse me. And the other one, this was already reported in ICDD, spring material. So this was used as a test. So we computed these two, and they were on the complex amount. So in that way, by first principles calculation, this predicted result was well confirmed. The similar examination work performed for 27 different compression pseudo-binary systems, and found that 23 among 27 compressions are located on the complex half, so it means they are thermodynamically stable by DFT. So this is quite satisfactory result, and our prediction without any prior knowledge, just by the arrangement of tensor element are well confirmed by DFT calculation. So we are quite happy with those results, and we put instead of giving all data to individual researchers, we put this data as an open database. So if you're interested, you can look at those pseudo-binary systems or others. It is available in GitHub. And of course, once these new CLC are somehow pointed out, we want to produce that new material by ourselves. But we are not 100% professional of material synthesis experiment. Rather than that, we call ourselves like a weekend cooker. We cook only on weekend just for hobby, that kind of thing. But for weekend cookers, synthesis of as yet unknown materials is quite difficult, because if it is known, then there is some kind of cooking, step-by-step cook, and then we can just follow that to produce that. But the synthesis recipe of as yet unknown compound is not given in this type of cooking book. So what we have to do is to ask the synthesis expert how they think, how to synthesize the material. But even for synthesis experts, for as yet unknown material, they cannot provide clear answer. They may say, well, probably it means high pressure to synthesize that, but high oxygen pressure to synthesize that, and so on. And the synthesis experts are not always have time to consult us. Instead, we try to use artificial intelligence, something like ChatGPT. If we can ask how to synthesize material to ChatGPT, and if they provide correct answer, well, of course it's fine. But for that purpose, probably we need a good source of data. That is the topics of the second part of my talk. This part was transferred from the second part of today's lecture to the first part. So this is a synthesis condition recommender system based on parallel experimental data. This was mainly done by this younger colleague, Hayashi. This is our weekend kitchen to try to synthesize materials in a parallel fashion. And this is called polymerized complex method. And the chemists may know this method, but if you're not familiar, let me explain a little bit. We prepare some solutions from the starting material. This contains, for example, element X, and this contains element Y, and this contains element A, B, C, and so on. And we use this type of robot to take predetermined amount of this liquid, like 1 milliliter or 5 milliliter, to make the desired mixture. And we use this type of robot to take 1 milliliter from here, 5 milliliter from here, and mix it in some of these places. But since we use this high temperature synthesis for ceramic materials, we have to put all of them into these crucibles. But they are all done by robot. Because it's weekend, nobody wants to work, so let's let robot do that work. And dry that, and then fire that high temperature. At the present moment, we do not have a robot to put it into the fire oven, so somebody should do that. After firing, also somebody have to take each of these crucible from the furnace and put it in a plate to examine automated powder X-ray diffraction. This can be done automatically, and so if we put 200 samples, these samples are automatically measured one by one. The next morning, we can get a series of this X-ray diffraction data. So we use not only polymerized complex method because this is some kind of special technique. This is quite universal, but for some purposes it is not very useful. And sometimes very traditional powder mixing method works better. So this is just an example of polymerized experiment. But let me explain with this method. For that purpose, so for polymerized complex method, for the starting material, we have chosen 28 elements from the periodic table. And also, I'm sorry, the small characters, but 32 starting materials, some of them are chloride, and some of them are some NO3 material, peroxide, and so on. Those 32 starting materials were used and made as this preparing solution. And for the target, as a weekend cookers, we cannot do nitride or phosphide, sulfide, those material which requires very careful treatment for handling. Instead, oxide materials are much easy to be synthesized, like using this type of furnace, conventional furnace. So we restrict ourselves for the oxide synthesis of oxide. So for 28 elements and 7 compressions, altogether the candidate compression becomes something like 10,000. So compression means 1 to 10, 1 to 9, 1 to 8, or something like that. Within this 10,000 chemical composition, this will correspond to the number of known compositions that is registered in ICDD PDF. This is the powder diffraction file. So among those 10,000, about 10%, 1,000 something are known compositions. So they are registered. But the rest 9,000 are unknown compositions. But this is oxide. And if you are working on oxide, you may know that just in the long history of the synthesis of such a binary oxide composed of such a simple element. So we thought from the very beginning that there may be very difficult to find something new in this zone because for more than 100 years there have been a lot of people examining those compressions, so there are not much left over, or possibly there are zero left over in this green zone. But we tried anyway. For these 10,000 chemical compositions, we have to use altogether something like 66,000 synthesis conditions. So about, again, 10% of these synthesis conditions correspond to this already known composition. The rest are corresponding to unknown composition. At the very beginning, we need some training data. So we have chosen these 1,500 conditions randomly from each of zone and to get the data, input data. Within this zone, we obtained more experimental data. This was also randomly chosen from this zone. And from this zone, we have chosen 619 data. And from this zone, although this synthesis condition corresponds to this already known compound, we found that 50% of them are only 50% are successful in the synthesis. The rest are failure in synthesis. It means, for example, for one particular composition, if you need 1,000 degrees C for synthesis, if we perform experiment at much lower temperature, like 700 degrees C, then you cannot synthesize that material successfully. So it ends up with a failure. So this is quite natural that we fail to synthesize by 50%. But in this area, which corresponds to the unknown composition, we failed to synthesize the target composition material by 100%, which means we succeeded 0%. So it is in agreement with our initial guess that it is very difficult to synthesize something new in this zone. But anyway, we took this 1,500 data as a training data and put it into the tensor decomposition technique. As a data for tensor decomposition, we used these X-ray results. Since X-ray results are automatically obtained by experiment. For example, this is for the target material with aluminum molybdenum oxide. And if the target material were successfully synthesized, we gave score 2, or we can choose any score as we want. We can give them 100 and 0 in the others. But anyway, in this case, 2 and 1. If it is unsuccessful, we get score 1. So this is an example that at lower temperature, 600 degrees C or 700 degrees C or 800 degrees C, we succeeded to synthesize material at a higher temperature. For some reason, it was not able to synthesize material. We do not examine the reason for the failure, but probably some sublimation of this dirty material or decomposition or many different kind of cases may exist. But anyway, we obtained these scores, and the score is will be standardized to be the standard within -1 and 1. So +1 corresponds to the successful synthesis condition, and -1 corresponds to unsuccessful conditions. So that is the reason why I thought that we can keep any kind of scores as we want. So we put all these data into the tensor. This is the tensor, and well, for simplicity, but actually we made force order tensor composed of number of elements, force order tensor with sturdy material number 1, number 2, and compression, firing temperature. This is force order, but let me explain third order. This is sturdy material number 1, sturdy material number 2, and compression. And if the result is successful, we get this orange from here. If it is not successful, then we get unsuccessful blue one here. This corresponds to the score +1 and the -1. But there are many unexperimented conditions shown by white color. And this is the original tensor. We decompose this tensor into this core tensor with 3 matrices to have this reconstructed tensor. So based on that, we can estimate the recommendation score for the unexperimented condition. So this is similar to the e-commerce to give the recommendation score for the unbought or not yet bought item. So for unexperimented conditions, some of them shows very good recommendation scores, some are not. And among them, we can rank the recommendation scores according to the obtained recommendation scores. And among them, among top 300, there are 135 conditions located in this zone. The rest of that 165 are located in this zone. Although this is corresponds to non-compression, we took randomly these conditions, so there are some of the conditions which were not yet experimented. But anyway, there are 135 conditions which shows good recommendation scores. That corresponds to 75 compression. This is smaller than this number because some material shows different conditions such as different temperature, which shows good recommendation scores. Anyway, we got this. And for all those 300 recommendation scores, we did synthesis experiment. So this is the result for the synthesis experiment. And this shows, the orange one shows the successful synthesis. Again, the blue one corresponds to the unsuccessful synthesis conditions. And the successful conditions are not always dominate the cases, but with the increase of the, the horizontal axis corresponds to the standardized predicted score. So with the increase of the predicted score, the rate of the successful result increase. So this is a fraction of successful condition with a standardized predictive score. With the increase of the predictive score, the fraction of successful condition increasing almost linearly. So it means the success rate is proportional to the recommendation score or predictive score. So if we perform these cases, then there is a good chance to find new material from the corresponding zone. But unfortunately, those of the showing high recommendation score are located within this no conversion. But there are some conversions which are not very high in predicted score, but still quite possible to get successful synthesis. Actually, among them, we found some new pseudo-binary, as yet unknown pseudo-binary conversion. For this lanthanum for vanadium to oxide, the recommendation score was something like that, 0.27 or 0.19. It is not extremely high, but with this condition, we were able to find something new, which are not yet reported, but we succeeded to synthesize that, and also we succeeded to characterize this material. And also for this lanthanum antimony containing material, we got this new material. So based on that type of analysis, we were successfully synthesized two material, two pseudo-binary oxide within this green zone, which we thought at the beginning is not possible to find anything new. The other weekend cookers, we are not professional of the synthesis, but with the use of the recommendation system, it was possible to find quite efficiently this type of compound. So this is the end of my talk, but using this type of recommendation system, it is not only useful to predict something theoretically, but also it is useful for the really synthesis of this type of new compound. And I think this is quite promising. So probably I leave some time for your questions. So this is the end of my talk. So if you have any questions, please do not hesitate to ask. Yeah, thank you. Please. You need a microphone?
Thanks again for this video. You did binary classification. Have you ever tried predictions like prediction systems? Recommendation systems for predictions? Can we use them? Is that
Recommendation system?
Or should we use this kind of technique for binary classification?
Oh, your question is, did I use classification technique for the synthesis experiment?
Your output was, if it succeeded, this is or not what? Either 0 or 1, right?
Well, you're talking about the synthesis results, synthesis experiment. Or for the, well, first part is for the prediction or for only from the database. And the second part is for the synthesis experiment. And which you're talking about? Or more general, second one?
The second one.
Second one, okay. And the question is, did I ever try the classification technique for synthesis experiment? Is that the question?
I understand that you look either 0 or 1. If the experiment is successful or not.
Yes.
Maybe there are 3 options for that in my case.
Can we use the same technique? Maybe I will listen.
Well, this was, in this case, sorry, 0 or plus 1 and 0 or plus 1 minus 1 or something like that. And it can also be used for the binary classification because the purpose is not to use this one, but the purpose is to predict the score of the unexperimented condition. So it's not necessary to put into the tensor. Instead, we can use binary classification technique as well. And I don't know which technique provides a better result. But in this case, we use tensor recommendation without any reason. And we didn't do the binary classification because binary classification, this tensor decomposition technique outperform quite nicely than binary classification. Binary classification is quite, say, simple way, and we thought this is more sophisticated, but it very much depends on the data, so we should be careful. And you're right, we have to compare many different kind of algorithms to get better result.
Thank you for your sharing information. In the first part of the presentation, I have just notified you intersect the 3 database at the same time. Why didn't you concentrate on the intersection points of the candidate compound database samples when you feed your training data? Just concentrate on the first just one database. If you, let's say, try your system with the intersection point compound, with the in the first theoretical part, not the synthesis part, in intersection of the 3 database, you showed presentation 13.
The first part.
Yeah, the first part.
So your question is why?
Yes. Springer method, the intersection point of the 3 sets. Why didn't you train your algorithm with the intersection samples? Yeah, the intersection point, because you are finding the similarities of the feature space with the 3 sets.
In this case now, yesterday's talk we used similarities, but here we do not use any similarities.
Yeah, I know,
well, from my viewpoint, this does not have any meaning. This is just by coincidence. This ICSD has this type of registry. ICDD has this registry. That's all.
But
no clear reason why.
for your tensor decomposition technique, if you train your data with the intersection points, wouldn't be better enhance your results more better than the case?
I do not understand your point because this was just used for the training set and the others are used for the test set. That's all. And this intersection or overlapping is just by coincidence. And,
I know. Normally, as a data scientist, if you train your algorithm with a more data, your system becomes more sophisticated and precise.
Yeah, right.
That's why I am
right. But we have so small number of data, so we cannot increase this so easily.
Okay.
Yeah. So if we can increase that easily, of course, by some kind of automated experiment, probably that will be possible to be increased. But at the present moment, it is not that easy.
What question?
Okay, thank you for your valuable presentation. I want to ask a question about your algorithm, general question. How to choose your algorithm for your data? Yeah, it's a good algorithm for my data. What's your criteria?
Well, that is a really good question. And the answer is we do not know. As I said, for this case, we did everything and found that they are better than the others. That's the only criteria. If the result is good, that is a good model. That is, I know this is not logical, but it works. And well, data scientists use it that way. But we should do much better, I think. But to test many different classifiers in this case is so easy. Using this scikit-learn, something like Python type of software, just put one line and instead of NN equal default linear SVM, then they perform that. So to test many different classifiers are so easy. So we just do that. Of course, there should be a good reason why it works for certain system and not. But again, it is very much dependent on the data quality and quantity of data. Also in this case, if there is more data in this area and more data in that area, then the result may be different. So again, we always have to test many different algorithms for the case of classifier and also for the recommender system in general. For example, binary classifiers, tensor decomposition or some other thing. There are many different kinds of techniques. So if we talk with data scientists, probably they have their opinion which is better and so on. But it's again very much dependent on the quantity and quality of data. So there is no universal solution for that at the present moment.
So perhaps we can take a break.
Yep.
As a